Greetings and welcome to this new semantic learning tree about astronomy. I've had this slide made for about a year and a half, and I have not produced a video about this because a semantic learning tree video is about 1 hour long, and it's a tremendous amount of work for relatively low return in terms of channel volume and traffic. However, I do want to make one more tree so that more people can be inspired to make trees about many other subjects. There's this poor fellow who keeps requesting over here that I make an electrical engineering semantic tree, and I would like to do that, but I don't know when I will get around to doing that, and it probably will not be soon enough for his immediate needs because he's very desperate. He requests it many times. In such a case, I think you should try to make your own tree and get other people who know about electrical engineering involved to give you feedback. And it doesn't have to be perfect. Just get it part of the way there, and then more people who know more about electrical engineering will help you. So do that if you're in a hurry to get a semantic learning tree. But this one is about astronomy, and I gave a lot of thought to what should be in the trunk and what should be in the thick branches versus the thin branches. Now, to understand how a semantic learning tree works, see the original video, which you can see in this tag up here, about how to build a semantic learning tree. And also see the one that I made before this, which was for paleontology, which you can see in this tag up here in the upper right-hand corner. Now, a bit about my own history with astronomy and how I got to know so much about it. I was always interested in space-oriented things, and I was fortunate enough that Carl Sagan's Cosmos came on when I was about 6 years old, and my father was interested in it, so I watched it with him. I've probably watched Carl Sagan's Cosmos many dozens of times. So that was 1980. And then, on March 10th of 1982, there was to be a very unique astronomical event called a syzygy. That's probably a word you've never heard of before, a syzygy, but that means that many planets are in alignment at once. And on March 10th, 1982, all planets were going to be on the same side of the sun in alignment. So that was a very unique historical event. And I was 8 years old at the time. And my father told me about it because he just saw it on the news and just passed that info along. But my expectation was, hey, we were going to go somewhere to see all the planets close together through a big telescope, even if that meant going some considerable distance. And my father wasn't interested in driving somewhere to do that. More importantly, that would have been very inconvenient, as I realized later on, because I lived in Cleveland, Ohio. This was March 10th. At night, it was always going to be cloudy in Cleveland, Ohio in March. But because it was cloudy on the night of March 10th, which was a Wednesday, a school night, I missed it. And I was 8 years old, and I cried. I cried in the middle of the night. At 3 a.m., I was crying because I thought that I had missed something that I would never see again. And the fact that I was 8 years old was very relevant because that is young enough to still cry about something like that, but old enough to recognize the gravity of missing something that was only going to happen once in your life or very few times in your life, and so forth. If I was only 4 or 5, I would not have cried about that, but if I was 10 or something, I would not have cried about it either. But since I was 8 years old, when this March 10th, 1982 syzygy occurred, I cried. And then, get ready to go to school the next day. None of the other kids knew or cared or anything like that. But I was a different type of kid, obviously. The magic of the modern age means one never has to miss something like that, because even if it's cloudy where you live because this is the winter, or if you don't own a powerful telescope, there are many people with powerful telescopes, including university telescopes, that simply live stream what is visible through their telescope onto YouTube, and then thousands of people can see the image at the same time. Much more recently, in 2020, there was a conjunction, which is much, much less profound than a syzygy. This is a conjunction of just two planets, Jupiter and Saturn, which appeared very close to each other in the sky in 2020. And one could look at it through a telescope, but if you don't have a powerful telescope, there were many powerful telescopes that were just live streaming the conjunction onto YouTube. So you don't care whether it's day or night or that you don't own a telescope, you can watch this on YouTube many to one. The other problem with a big telescope is that you have to share it with a lot of people. In 1986, I was looking at Halley's Comet, and that was unfortunately one of the worst years to view Halley's Comet relative to all historical passings of Halley's Comet every 76 years, because this is when the tail was the furthest away from the Earth relative to other recent passes, such as in 1910. And I went to a place where we were looking at it through a telescope, but then too many people were sharing the telescopes. You had to wait for your turn and then tell someone who was hogging the telescope to, hey, move on, let somebody else see it and all that. All of those bottlenecks are gone in the information age under my atom thesis, third millennium economics, because now there's the ability for 1 million people to look through the same telescope without leaving their homes and have access to much more powerful telescopes than not only you could ever privately own, but you might have had to drive a very long distance even to be able to see through such a telescope in the past, when you have to share it with 100 different people and tell people who are hogging it to get off and let someone else see. Now you don't have to do that through the magic of the internet and the information age, third millennium economics. But I digress. That is how I came to know about these 4 things that are the trunk. And learning about these 4 is foundational to every aspect of astronomy, whether nearby astronomy, the moon and nearby planets like Venus and Mars, or the furthest edges of the observable universe. But to begin, we have to get to the very basic foundational concepts, which is awareness that the moon goes around the Earth and the Earth goes around the sun, and you'd be surprised how many people don't know that. There was recently a poll in the United States indicating that only 70% of the people know that the Earth goes around the sun in 1 year. That is at least an improvement relative to 30 years ago, when a similar poll indicated only 50% of people knew that. And then when they did a gender breakdown, well, let's just say that it is unpublishable what the gender breakdown was for awareness of the Earth going around the sun in 1 year. But those are the basics. Then the totality of the solar system. You should know the names of the planets and what the large moons of the major planets are. A lot of older Americans who are of average intelligence are very emotional about the fact that Pluto is no longer considered a planet, when, for every scientifically logical reason, it makes sense that Pluto got demoted out of planetary status. But some people are very emotional about that, even though they don't know anything else about Pluto. Time frames of the cosmos. You can see Carl Sagan's cosmic calendar for a description of this. Cosmic distance. Get some basic idea about how far apart certain objects are, because then you will get a sense of the proportionality of the size of the solar system, of the galaxy, of the universe. And then let's put aside these 2 side branches for the moment, human observation of space and physics, and go to these 3 red categories: individual objects in the solar system and beyond, star types, and multi-star systems. To learn how to advance through that, we will go to my tutorial of Celestia, which is a free astronomy-oriented software that you can download, and it can really be very useful in speeding up one's knowledge of astronomy. So let us proceed to my Celestia tutorial and then come back to the Semantic Learning Tree. So here is my basic Celestia tutorial. So once you download the Celestia software and open it up, you will get this that zooms up in front of you. And where do you go from here? So you go to Navigation, go to Object. The default is at the Earth, but you can choose the latitude and longitude of the point you are above, as well as the distance. So let's say we want to be above the North Pole. The latitude is 90. Longitude doesn't matter quite yet. We'll come back to that later. And let's say you want to be 10 Earth radius above that point. So you type in 10. And you just do go to. Okay, so you're observing the Earth from above the North Pole, 10 radii above that. Now let's say you want to be further up to the extent that you can see the moon and the moon's orbit. So for that, you have to go much more than 10 Earth radii. Let's say 100 Earth radii. Is that enough? No, it was not. Let's say you go 1,000 Earth radii. Is that enough? Yes, it was. And you saw that this moon comes here. But the moon is not labeled and the orbit is not visible. So what we do is minimize this, and we go to Render and View Options. And let's see what we want to check over here. We already have orbits of stars and planets visible, but how about labels for moons and orbits for moons? See, now you have both the moon and its orbit, and you will get the same for the moons of Jupiter, Saturn, etc. So that's 1,000 Earth radii. Now we go back to navigation, go to, maybe 1,000 was too much. Let's go to 300 Earth radii. Okay, 300 Earth radii. You can see the entirety of the moon's orbit. This is the moon, this is the Earth, and the distance. Now, another distance option is AU, astronomical unit. 1 astronomical unit is the distance between the Earth and the Sun. So this is still very little in terms of AU. We use that at the planetary level rather than at the distance between the Earth and the moon, that level. Humans have been to the moon and back. That's how near the moon is. Humans have never been further than the moon, and extremely few humans have ever been to the moon. In fact, none after 1973. But yeah, some humans have been to the moon, about 12. So now we'll go to another planet, Jupiter. And we will also look at Jupiter from its north pole. But as Jupiter is much bigger and has many moons, we are going to do AU for that. So instead of 300 radii of Jupiter, and Jupiter's radius, of course, is much more than that of the Earth, we are going to look at Jupiter from a distance of 1 AU, and the orbits of Jupiter's moons will be visible. Longitude, again, doesn't really matter quite yet. I'll talk about that later. So we go to that, which is elsewhere in the solar system. So 1 AU is too far, even for the entirety of the Jupiter system. So we are going to do less than 1 AU. Let's do 0.2 AU, so 5 times closer. Now we're getting somewhere. We're seeing the 4 major moons of Jupiter, Callisto being the furthest out, then Ganymede, Europa, and Io. At 0.2 AU, we can see this. Now we're only selecting the major moons because Jupiter has 4 large moons and many dozen smaller moons. So if we want to see the orbits of the smaller moons, we go to Render again, View Options, Minor Moons, both labels, you can see how many there are, labels, and orbits. That's a lot of orbits. So okay, and now from navigation, we go to Object again, and maybe this time, being 1 AU from Jupiter is not too far. Okay, so even at 1 astronomical unit, which is a very large distance, the Earth and the Moon would not seem far enough apart, even in Celestia, to be easily distinguishable from 1 AU. The Jupiter system is this big, meaning there are a bunch of small moons and dozens of them that are much, much further away from Jupiter than Callisto because of Jupiter's high mass and its gravity. Its Hill sphere, one of the terms that you'll see back in the tree, the Hill sphere of Jupiter is very large because of its high gravity, even though it is not that far from the Sun, certainly closer to the Sun than Saturn, Uranus, and Neptune. Now we shall go to Saturn at the same 1 AU distance. Yep, the Saturnian system also has a lot of minor moons, much further away from Saturn than the bigger moons, but we shall go to a closer distance of 0.1 AU. Now we can see bigger moons, including well-known ones like Titan, and even Saturn itself with its rings. Do we want to see the rings of Saturn more closely? Then we go closer than many of the moons to 1/100th of an AU, which is still a lot of kilometers. 0.01 AU shows us the rings of Saturn from above, so we can see the rings are obviously not touching Saturn because we're looking at it from above rather than from the side. The distance is 1,496,000 kilometers, which is 1/100th of an astronomical unit. The radius of Saturn is this much. Now, if you want to see the rings from a different angle, this is where you adjust the latitude. So instead of 90th latitude, meaning the North Pole, let's just say 80th latitude. Okay, a bit of an angle. How about 60th latitude? Okay, now you can see the rings from somewhat of an angle and the shadow of Saturn onto its rings indicated by where the Sun is. And this is all real time. This is what Saturn is currently at this very moment. It's not what Saturn was like a year ago, because the position of each moon is correct relative to its orbit. The closer moons will actually move quickly, so if you come back after an hour or two, you'll see a slight change in its movement, although Jupiter is a better place to do something like that. You could do it here at Saturn as well. So now to view this more closely, let's get rid of the moon orbits, render, view options, orbits of minor moons, and even major moons. Okay, so now only the labels of moons exist, but not the orbits. See that? So even the big moons like Titan, etc., don't have their orbit here. This is Saturn, as we can see from some angle. So you can do this with all sorts of celestial objects in this Celestia software, and you can do this all over the place in our solar system once you get a basic idea about what would be the right distance. Always start with radii so that the absolute number of kilometers is not something you have to get an intuitive sense for. But 10 radii from Earth is very different than 10 radii from Jupiter. Once you get an idea about the proportional distance between planets and the size of each planet's system, then you can choose absolute units like kilometers, or preferably astronomical units, because you'll have an idea whether it should be 0.01 AU, 0.1 AU, 1 AU, 10 AU, and so forth. And speaking of 10 AU, let's look at the entirety of the solar system with just the planetary orbits. So we again go to navigation, go to object. We go to the sun, which is known as SOL, Sol. We'll again take a latitude of 90, so the north pole of the sun. And the AU we're going to take to see the entire system is first 40 AU. This will not accommodate the outermost planets, but at least we'll still see the Earth. And longitude, again, doesn't matter quite yet, so we'll do this, go to this. Okay, there we go. Sol, Mercury, Venus, Earth. This is the Earth's orbit over here, and where Earth is Mars, and then outer planets, Jupiter, Saturn, Uranus, and Neptune. But at 40 AU, we cannot get the entirety of Neptune's orbit. To get the entirety of Neptune's orbit, which is 30 times further away from the sun than the Earth is, we have to go further to the extent that the Earth's orbit will no longer be visible. So we're going to go to 70 AU, 70 times the distance between the Earth and the sun. Okay, so Neptune is visible, not the entirety of its orbit, but you get the idea of what its orbital circle is like, and Neptune itself is here, Uranus is here, Saturn and Jupiter. Earth's orbit is barely visible at all. If I go even slightly further away, from 70 AU to 80 AU away, you still can't fit all of Neptune's orbit into this screen, but now the Earth's orbit is not even visible, let alone the Earth itself. Now to wrap up this tutorial, I'm going to show you a different star system. So we're going to go to Alpha Centauri, which is actually a triple star system, 2 yellow stars similar to the sun in size and type that are somewhat close together, and then a very small red star that is so far away that it will not fit in the same screen for our purposes, but that happens to be the closest star to us, not counting the sun, but it's so dim that it's still not visible by a long shot despite being the closest star because it is a dim red dwarf star. So we're going to go Alpha Centauri A because there's 2 stars. Latitude can be 90, longitude, this is where longitude will be useful, we'll find out. And distance, 80 AU from that. But remember, this is 4.5 light years from the sun. So as soon as I type go to, we're about to travel at much faster than the speed of light to go to this other star system. So go to. So I typed in just Alpha Centauri because I didn't want to center around one of the 2 stars, but rather the median barycenter of the 2 stars. So Rigel Kentaurus A, Rigel Kentaurus B. That's the same name as Alpha Centauri. That is very confusing, but Celestia accounts for both of these names. You can also call it Ptoleman or Gliese 559. Confusing, but as long as you remember one name, you're doing well enough. Now, these are 2 stars, one a little bit bigger than the other, and they orbit each other over a time span of 80 years. At the closest point, they are maybe 11 astronomical units apart. At the furthest point, as far as 40 astronomical units apart. But we are at the barycenter of both. Therefore, to see these orbital rings from a better angle, we have to adjust this longitude to get some positioning. And this takes a bit of trial and error until you get enough spatial practice. So what I'm going to do is take a latitude of 0, so the equator, so 90 we're going all the way to 0, and this longitude, let's do minus 40. And don't worry about memorizing how to do this. You can do this through trial and error as well. Okay, we just moved around to a different angle, and we can see this dual star system. Two stars that are similar to the Sun. Rigel Kentaurus A, Alpha Centauri A, is slightly larger than the Sun, but still a yellow star. It could host Earth-like planets in the life zone around it. And then Rigel Kentaurus B, which is a little bit smaller than the Sun. And therefore it has a larger orbit because gravitationally it's less powerful than its larger sibling. But both of these orbits complete over a period of about 80 years. And like I said, Proxima Centauri is a small red dwarf star that orbits these two from much, much, much further away, like 0.2 of a light year away. Now, this is a distance of 80 astronomical units, and we saw what our own solar system looked like from 80 astronomical units, so we can go a little closer, 50 astronomical units. These stars may have planets around them, but we have not discovered those yet. We have discovered planets around Proxima Centauri, but not around either of these two, which is a little bit surprising given that these are near. But nonetheless, we don't know about planets around these stars for sure. That's why we don't have planetary rings. Now, the gravitational effects of both of these stars are quite powerful because both are roughly similar to the Sun in size, one a little bit bigger, one a little bit smaller. Therefore, they can't have planets that go near the other star. Therefore, they can only have planets within about 2 astronomical units. The Hill sphere of each of these stars is only about this much around each. But the life zone around each of these planets is close enough to each of these two stars that the other star would not interfere with it. So it is possible to have a planet that orbits within a temperature zone similar to what Earth orbits the Sun at. And I could go for many hours in Celestia to teach you about all the various star systems, but this is a tree. I'm just teaching you a technique of what to look up. You could look up all types of other nearby star systems, binary and triple star systems, but that is not the purpose of the tree, just the technique. So this concludes the Celestia tutorial, and we go back to the tree. Okay, now back to the tree. As we saw from Celestia, the Earth's relationship to other objects is important. A person should have a general idea about how far the moon is from the Earth and how far the Earth is from the Sun and how far apart individual planets are. Way too many people don't even know that much. The structure of the solar system with approximate distances, of course, is important. Time frames of the cosmos, meaning that the universe began about 14 billion years ago in the Big Bang event that is well known, and how long the Earth has been around. A lot of people don't know how long the Earth has been around and that life began shortly thereafter the formation of the Earth. Then cosmic distance, as measured by how much distance light can travel in a given time. The moon is about 1.3 light seconds from the Earth. The Sun is about 8.5 light minutes, and the nearest star is 4.2 light years, and that is a member of that Alpha Centauri star system that we just saw in Celestia. So this is the core. You can't know anything about astronomy unless you are well versed in at least these 4 things. From this point, we can go to the smaller branches. We shall go in a clockwise manner. Human observation of space. 5 planets have been known since antiquity, which are Mercury, Venus, Mars, Jupiter, and Saturn, because those are visible with the naked eye and had an unusual motion relative to the stars. They were moving fast, whereas the stars were not moving a significant amount during a human lifetime. The 7th planet, Uranus, was one that was observed but not identified as a planet due to how dim it was and its slow movement. So observers were unsure about whether that was a planet or not. And Neptune was never visible from Earth with the naked eye. Then major historical events, like, for example, when was Neptune discovered? When was the first satellite launched into space? And that would be Sputnik from the Soviet Union. When was the first man on the moon? We know about that very well. When was the last man on the moon? That was also in around 1973 or so, because we only sent humans to the moon during a brief 4-year window or so. Then from here you get to the smaller branches like near-Earth objects. one aspect of astronomy that can affect people's day-to-day lives is if an asteroid hits, and being aware of what the near-Earth object situation is. And I have many videos about that, such as what you can see in this video here in the upper right-hand corner, along with other mitigation strategies for asteroid impact. And then you get to these topmost branches, such as the names of famous astronomers: Copernicus, Galileo, Tycho Brahe, and others, William Herschel. You should have some idea of what the 3 or 4 top astronomers are known for. You don't necessarily have to go any deeper than that, but you should know who did what. Asteroid mining, which could be of considerable commercial importance, and I have videos about that on this channel as well, because many precious metals are actually more abundant in asteroids than on the Earth, because asteroids are smaller, so the heavy metals could not sink to the center of the asteroid like all the heavy metals, such as gold, sank to the center of the Earth and are not accessible. And then asteroid impact defense, which I talked about with these near-Earth objects. What are our strategies for mitigating asteroid impact in terms of detection, as well as diversion, and best case, capturing them, because they also have valuable metals and other compounds in them. Now, as we go back to major historical events, the thicker branch, then we go to here. Remember, don't jump from asteroid impact defense just to individual missions. You have to see it in the context of this branch, which was in the context of this branch, and then the context of this to the trunk, as always. That's how this semantic learning tree works. Human space programs, the first satellite, like we talked about, Sputnik. The Apollo program, the United States sending men to the moon. The Voyager program, where the United States sent probes to outer planets, all the way up to Neptune. The New Horizons spacecraft that reached Pluto. Major space telescopes, like the Hubble Space Telescope and the James Webb Space Telescope. Things like that, and that will lead you to a comprehensive knowledge of individual missions. There are many good graphics on the internet that chronicle these individual missions in terms of what year they were launched, where they went, and things like that. Now back to human observation of space. What is our galactic neighborhood? So beyond just observing our own solar system, what are the stars we can see in the night sky? What are the constellations? The Orion constellation is the most visible from everywhere. And then we get to individual star identification. If you look at the constellation Orion, which is the easiest one to identify in the sky and is visible most of the time, you will see all of the bright stars that form that constellation. How Rigel is one corner of the Orion constellation. Betelgeuse is the opposite corner of the Orion constellation. The rightmost star in the belt is another blue giant star, Mintaka, and so forth. And then there are other well-known constellations like the Big Dipper, and you can identify some of the stars in that. If you're familiar with the stars in these two, Orion and the Big Dipper, you're doing pretty well. You know more than most people. There are, of course, other constellations beyond that, and other formations to look at, like the Pleiades, for example. But that doesn't take that long. That's a relatively easy thing to see. But you'll feel good when you can identify the stars in common constellations, and you know their approximate distances. Like the two corners of Orion, Rigel and Betelgeuse, are both very far away. Rigel is about 800 light years away. Betelgeuse is around 650 light years away. Now back to this thing, individual objects, star types, stellar classes, and multi-star system. Star types is a complicated field because there are some stars that are much smaller than the sun in volume. The smaller a star gets, the higher its density becomes. And the larger a star gets, the lower its density becomes. But luminosity also rises in proportion to volume, of course, in part because there's more surface area in that case. And while blue stars are usually larger than the sun, like Sirius is a blue star but not a giant, but Rigel is a blue star that is a giant. Whereas with red stars, you have red supergiants like Betelgeuse and Antares, some of the largest stars in diameter, and among the few stars that are large enough to photograph as a disk from the Earth, which is not possible even with the 3 stars in the Alpha Centauri star system, despite that being the nearest star system, because their angular diameter, their apparent size from Earth, is less than that of Betelgeuse or Antares. But then as you get to smaller types of stars, the sun being a yellow-orange type of star, you get orange-red type stars, which are known as K-type stars. And then there is a letter code in terms of star size. G is the category that the sun belongs to. Higher than G are ones like O and F. Lower than G are ones like K, which are often considered the most suitable for life because they have a longer lifespan than yellow stars like the sun, but are also low enough in density that planets in the life zone are not likely to be tidally locked, and I'll tell you what that means in a minute. Then the smallest stars, which are the red dwarfs like Proxima Centauri, Barnard Star, and Wolf 359. even though Proxima Centauri is the nearest star to our solar system, is far below the luminosity where we could even see it. Therefore, the nearest star to us is one that's still too dim to see. It has a luminosity in visible light of less than 1/20,000th that of the sun, although it's much denser than the sun, and therefore its mass is non-trivial. And then these are just the stars that we can see. The Milky Way galaxy has an incredible number of stars, more than 200 billion by many estimates, and that's just our galaxy. There are satellite galaxies that orbit our own galaxy. There are several of these, in fact, like the Large Magellanic Cloud and also the Small Magellanic Cloud. So there are several of these. So the nearest galaxy is, in fact, a galaxy that orbits the Milky Way galaxy. It's a smaller galaxy. However, the nearest independent galaxy is the Andromeda galaxy, which is larger than the Milky Way and 2 million light years away. So while the diameter of the Milky Way galaxy is 100,000 light years, about 20 of those diameters is the distance between the Andromeda galaxy and the Milky Way galaxy. And these intergalactic distances are so vast that even in Star Trek, for example, in the 24th century version of Star Trek, they travel between nearby stars very quickly, almost as though it's just a few days' journey to go 50 light years or something because of their faster-than-light warp travel. However, the other side of the galaxy is still so far away that it would be considered 70 years worth of travel to go from one side of the galaxy to the other, as was the entire premise of the Star Trek Voyager series, as well as the distance that was covered by the Bajoran wormhole in Star Trek Deep Space Nine, and how the wormhole put into contact two parts of the galaxy that were 70,000 light years apart and thus could have only been traveled in 70 years or so. And that is so intergalaxy. No one in Star Trek talks about regular transportation to another galaxy. There's a great galactic barrier that prevents their ships from even leaving, but it's also too far. So everything that happened in Star Trek is still within the Milky Way galaxy, with the further parts of the Milky Way galaxy still being considered extremely far. And yet there are hundreds of billions of galaxies in the entire universe. Our nearby galaxies are called the local group. So that's the Andromeda galaxy, and then the next nearest large galaxy known as the Triangulum galaxy, which is in fact the furthest entity visible with the naked eye from the Earth because it's 3 million light years away, and so on. But there are hundreds of billions of galaxies. And the entire width of the universe is about 93 billion light years, as all these galaxies are moving outward. Now, the Big Bang was about 14 billion years ago, yet the width of the galaxy implies a radius much larger than that because it's 93 billion light years apart. So even from the center, why is the extremity a good 46.5 billion light years away? So there are videos on the internet that describe why the diameter of the galaxy is more than the furthest apart galaxies could have traveled at the speed of light. But the Big Bang was the origin of time as we know it and of our universe as we know it. Now, what existed before that? What existed 20 billion years ago? What existed 30 billion years ago? Well, there are cosmologists and astrophysicists that struggle with that question, and nobody knows the answer to that because, as far as we are concerned, time began 14 billion years ago, and what was there before that, we can only guess. Okay, so now we go back to these core branches here: individual objects, star types, and multi-star systems. Our sun is a solitary star. We are not part of a two-star system. However, many stars are part of 2 or even 3-star systems. Alpha Centauri, yet again, is an example. It's a 3-star system. Other nearby star systems, such as Sirius and 61 Cygni, are also 2-star systems. Sometimes the stars are almost identical in size, stellar classification, and luminosity, as is the case with 61 Cygni, or the first 2 stars, Alpha Centauri A and B, in that star system. Sometimes they're very different. In the Sirius star system, you have the bluish-white star that we see in the night sky, the brightest star visible to us, but it also has a white dwarf companion that is way too dim for us to ever see, but nonetheless is super dense and has a lot of mass, and therefore even that is a star system with a peculiar orbit of 2 very massive objects orbiting each other, and you can look at that in Celestia. SETI, the search for extraterrestrial intelligence. That is something that has been going on for a few decades, but I wrote an important article way back in 2009 saying that, well, computational power is expanding a lot, and we'll talk about that in a minute. Then, of course, any searching done through SETI leads us to the subject of exoplanets, the discovery of which is rising exponentially, and I have videos about that on this channel, such as what you see in the upper right-hand corner here. We now know of about 6,000 exoplanets, and we could easily find more just by launching more telescopes to look at other parts of the sky. But our telescopic capability is rising because of computational progress. Therefore, what we can discover is also increasing in resolution. Remember, whatever comes through a telescope is data. Therefore, as computational power increases, the resolution of that data can also increase, which is why we can see more and more stars as disks and see their surface, which is not possible until the beginning of the 21st century for the most part. And we can also discover exoplanets, which also were very, very few in any confirmed discoveries until the 21st century, which then leads us to the Drake equation. What is the probability of extraterrestrial intelligence in our galaxy? We're not even going to the rest of the universe because that's just too far away. We're just talking about our galaxy, which is, again, already huge, 200 billion stars. We should worry about discovering intelligent life within our galaxy before we worry about anything outside of our galaxy. Because like I said, even the 24th century fictional universe, as described in Star Trek, is not really the universe. It's just our galaxy and little to no observation or contact outside of our galaxy. And then you have SETI and the singularity, where I tie together two seemingly disparate disciplines because the notion of a technological singularity actually conflicts somewhat with the idea that there are many, many intelligent civilizations in our own galaxy, because our computational power and thus our capacity to detect them is rising exponentially, as well as the cumulative timeline of our own existence, which increases the probability of other civilizations having been around long enough and surviving long enough for us to discover them. So I consider that an extremely important article because these two communities don't interact that much with each other. The SETI community and the technological singularity enthusiasts. Ray Kurzweil writes a little bit about this, but not that much. And I say that by a relatively near year, 2030 or so, if we don't find any evidence of any intelligent life in our galaxy, then we have to start to consider what can often be called the Fermi paradox, the rare earth hypothesis, and so forth, that we might very well be the first. There could be many that are less advanced than us, but the odds that there are some more advanced than us is falling. We don't have enough data yet, but you should read this entire article and my video on this channel about SETI and the singularity, which you can see in this tag up here, because I wrote that in 2009, and now, 2025, we have still found exactly zero evidence of extraterrestrial intelligence. We're still very early in our data detection, but the more time passes, the less likely that there are so many intelligent life forms in our galaxy. Like, for example, in Star Trek, every 10 or 15 light years in every direction is an intelligent civilization that originated from a planet. Even the founding members of the United Federation of Planets all come from stars that we know of that are less than 16 light years from the Earth. And clearly, there isn't that density of intelligent life from what we have discovered so far in our immediate neighborhood of our galaxy. Now, why do I have something called life zones tying to three different parts of the semantic learning tree? Because to understand the concept of life zones, you have to understand various things that are not directly connected, such as stellar classes, while life zones pretty much only exist under our current understanding of life around G, K, and maybe the upper range of M red dwarf stars. Recognizing how few stars might have a life zone is a component of the Drake equation. And then among smaller stars and planets too close, the temperature might be right, but then we have a problem of tidal locking, which means the same face always faces the star, and thus the temperate zone is only the horizon band of the planet, which could still be 10 or 15% of the planet's area, but I'll talk about that when we get to this branch over here. But make a mental note of this life zones and how it connects to all three of these things, because you'll only understand the totality of this subject once you get to all of this. So now going all the way back down to where the trunk begins to branch, physics. A situation commonly like the Big Bang Theory actually did a lot to educate regular people about certain types of astrophysics and physics concepts, at least if you look up terms that were brought up in the show, because to their credit, they tried to be accurate scientifically as much as possible. So that situation commonly did not make the same mistake that Star Wars made in saying parsecs was a unit of time when it's in fact a unit of distance. That's something Han Solo said in 1977, but that was before the internet age. Now, any type of output in science, technology, and especially physics has to be more scientifically accurate. So when you get to inter-object physics over here, then you understand things like tidal locking. The moon is tidally locked to the Earth in a 1-to-1 resonance, which is the only valid type of tidal locking. People say that 3-to-2 resonance is a type of tidal locking, but I say that for practical purposes doesn't really matter because the same face is not always facing the heat object. And that matters if the superior object is a star that radiates its own heat and light. But the moon is tidally locked to the Earth because Earth's gravity is enough that the same face of the moon is always facing the Earth, and the far side of the moon was not seen until a probe went all the way to the other side of it, which means the 1960s. Humans never knew what the other side of the moon looked like until the 1960s. There are still people alive today who were born when humanity had no idea what the other side of the moon looked like. Most moons in our solar system are also tidally locked to the planet that they orbit, except for very far moons. So all 4 of the Galilean moons of Jupiter are tidally locked to Jupiter. Titan is tidally locked to Saturn, and so forth. Now that's fine. That just means that one face is always facing the planet. If you are on any of the moons that I mentioned of Jupiter or Saturn, to see the main planet, you would have to be on the side facing it. On the far side, you would never ever see Jupiter or Saturn or whatever the primary planet the moon is orbiting. So that leads to a subject of orbital mechanics. And therefore, you have to look up things like tidal forces, eccentricity, and gravity wells. You should look at the Wikipedia pages for each. Tidal forces are the gravitational pull on parts of a body from another body. Our oceans have tides because the moon's gravity is pulling the water towards the moon, meaning high tide. And then when the moon is in a different location, the tide recedes because Earth rotated, and therefore the moon is pulling it in a different direction, low tide. This also causes gravitational pull on the internal tectonic plates of the Earth and is one of the factors in earthquakes. The moon is pulling one plate and not the other, causing a shift. And the sun's gravity also matters here too. Eccentricity. So why is Mercury not tidally locked to the sun in a 1-1 resonance? Yes, it is tidally locked in a 3-2 resonance, but that doesn't matter quite as much because the same face of Mercury is not always facing the sun. Therefore, it doesn't become super hot while the faraway face becomes super cold because it never sees the sun. So Mercury's orbit has a 22% eccentricity, which is why it's not 1-to-1 tidally locked to the sun. But some orbits are very eccentric, like Pluto's orbit around the sun is quite eccentric, as opposed to being circular. The opposite of eccentricity is circular orbits. A perfectly circular orbit has no eccentricity versus a very elongated one has high eccentricity. Take, for example, Halley's Comet, which has extremely high eccentricity, which is why we only see it once every 76 years, for example. And then gravity wells. Why is it that when we need to send a probe to Neptune or Pluto, there's always a visit to Jupiter and something called the slingshot effect? Because using Jupiter's very high gravity for that reason can accelerate such a probe if you slingshot the effect very, very well. Which is also why in a film like Star Trek IV, where the crew of the Enterprise want to go back in time 300 years to 1986 and back again, they use the gravity well of the sun to accomplish that slingshotting effect to go faster than the speed of light. So these are orbital mechanics that you can study. You don't have to know everything about them, but you just have to know what they mean. And then getting back to here, back to physics, we already did inter-object physics and some concepts that overlap with observational physics. So we again go to physics and observational physics. Hill spheres. It's part of orbital mechanics for sure, but what is a hill sphere? How far could the moon be from the Earth before it would no longer orbit the Earth but orbit the sun? The gravitational limit of the Earth is thus the hill sphere. And we saw some examples of the hill sphere for Jupiter and Saturn when we did that Celestia tutorial earlier. Similarly, the sun has a hill sphere beyond which the sun's gravity is no longer the dominant gravity, and the gravity of whatever nearer star in that direction exists is the dominant gravity, and this can adjust based on whether that star system is more massive than the sun or not. The Alpha Centauri star system is 3 stars, and therefore about 2.2 times the sun's mass in total. Therefore, the point at which the sun's hill sphere ends and Alpha Centauri's hill sphere begins in the line connecting the two is much less than halfway between the two. It's actually closer to the sun. However, there are directions where there is no star for a much longer distance, and therefore the sun's hill sphere in this instance extends further than that in that particular direction. Now, stars are also moving all the time. Therefore, a stable orbit around the sun is pretty much limited to 1 light year based on the positions of all the stars now and where they might be for the next few tens of thousands of years. That is what the hill sphere is. The moon also has a little hill sphere, which means the distance up to which a small satellite would orbit the moon rather than the Earth, for example. So this is part of observational physics. And then back to observational physics, we go into things that are now more visible in terms of light. Now we have to talk about magnitudes and as relates to the luminosity of stars. There are two types of magnitude: absolute magnitude and apparent magnitude. Absolute magnitude is how bright a body would be at a fixed distance of 10 parsecs, which is 32.6 light years. Stars like Rigel and Betelgeuse would appear much brighter than they are now at this distance because they are presently much further than that, where the sun would be very dim at that distance. 32.6 light years. Now, here's the funny thing about magnitudes that confuse a lot of people. The higher number is dimmer in the positive, and then as the number gets lower and goes into negative values, it is brighter. And 5 whole numbers apart represents 100x of a brightness change. Therefore, if the absolute magnitude of something is 0, something that is plus 5, like the sun would be at 32.6 light years, is 100 times dimmer. Whereas something that is minus 5 is 100 times brighter, and therefore minus 5 is 10,000 times brighter than plus 5. Okay, so that is the way to look at absolute magnitude, not apparent magnitude, which I'll talk about in a minute. Luminosity is the inherent luminosity of a star, usually measured in relation to the sun. Like Rigel or Betelgeuse is 60,000 to 120,000 times, and that's why its absolute magnitude would indicate a luminosity that much higher than the sun's. Whereas the nearest star, Proxima Centauri, has a luminosity in visible light that is only 1/20,000th of the sun. That's why it's not visible with the naked eye, even though it is the nearest star to us. The sun is 20,000 times more luminous than Proxima Centauri. So this translates into magnitudes. Now again, absolute magnitude is the standard distance, but then we also have something called apparent magnitude. The sun is very bright to us on Earth in apparent magnitude. It's the brightest object in the sky by far because we're so near. We orbit the sun and we're only 8.5 light minutes away. If we were 32.6 light years from the sun, it would only be plus 5, barely bright enough to even see. Proxima Centauri does not become visible until you are within maybe 2/10 of a light year of that star. So you have to get that near just to even see it at a super dim level. It is really that dim. Whereas stars such as Rigel, Betelgeuse, Deneb are so luminous that they're visible even from 600, 800, 1,500 light years away in the case of Deneb. There are many tens of thousands or even hundreds of thousands of stars closer than those that are not visible because their inherent luminosity is lower. Now, in magnitude, we'll also talk about a term called apparent magnitude. Now, in apparent magnitude, it's just what you see. That's why the sun is visible at such a high magnitude, meaning a large negative number, minus 23 or so, because of its brightness. A full moon is around minus 13 apparent magnitude because it's the second brightest object in the sky, even though it is only 1/400,000th as bright as the sun, and a full moon is only reflecting light from the sun itself. And then other planets have an apparent magnitude. Mercury, Venus, Mars, Jupiter, and Saturn are visible with the naked eye. Other planets are usually not. Uranus and Neptune are not because they receive too little light and are too far away and are pretty much never visible. Neptune is never visible. Uranus is occasionally visible if you know exactly where to look under the best conditions. And that's how you can take extreme examples. I mean, the brightest stars that exist in our galaxy, and some are so bright that we can see them even if they're in another galaxy, are millions of times more luminous than the sun. There's nothing that bright that is near to us, but there are stars that bright. There are other objects such as quasars, which are, again, many millions of times brighter than the sun. But that is why it's important to understand the difference between absolute magnitude and apparent magnitude. Anyone with a telescope on the ground only cares about apparent magnitude, of course, if you want to actually look at something. But if you want to know how bright and how big a star is, or how small and how dim a star is, you care about absolute magnitude as well. Then drawing this to the close, it's important to know about the major discoveries and claims to fame of the important astrophysicists: Isaac Newton, Albert Einstein, Stephen Hawking, Subramaniam Chandrasekhar. What they discovered. You don't have to go deeper than maybe these 3 or 4, but these are the giants of astrophysics. And then telescope basics, like what is the magnitude of a telescope? How does a telescope work? What type of telescope is likely to give you what amount of observational reach and things like that. I mean, I had one of those Jason Empire tripod telescopes when I was a kid, And it was useful, but there are only 3 or 4 things to actually look at, such as the moon, Venus, Jupiter, and a few other things. So ultimately, having your own amateur telescope isn't such a great thing. You might as well go to your local observatory, which is going to be a much more powerful dome-based telescope, or, like I said at the beginning of this semantic learning tree, just look at live streams on YouTube and elsewhere of people with much more powerful telescopes or institutional telescopes live streaming that on YouTube so millions of people can look through the telescope at once, especially for things that you can only see in the southern hemisphere, which you're not going to travel to. Okay, this is the semantic learning tree for astronomy, and I think this is the last one I'm going to do in this much detail, because now with all these LLMs like Grok and ChatGPT, it's easier for you to make your own with virtually any subject, and I'm not going to do many others in the same amount of detail. But I guarantee that you could be tremendously knowledgeable in the subject of astronomy in just 72 hours worth of time. And I mean 72 hours of actual study, not 3 days where you study just 3 hours per day, meaning 9 hours. 72 hours, you can do all of this. Always have the tree open in one monitor, and then the other monitor is where you go from Wikipedia to Celestia to maybe other websites or resources that are useful and so forth. Always use ChatGPT and Grok to ask questions about certain things you're confused about. 3-2, such as what the difference between 3-2 orbital resonance and 1-1 orbital resonance, or why a red star is cooler than a blue star, and things like that. You could have those LLMs open as well, and that will help in your learning process. And that's a new tool that has emerged more recently than my channel has even existed, and thus has come into existence as a tool after my original Elon Musk semantic learning tree video. And again, you can become an expert in a very short time with a tree like this. Thank you very much for watching.